What's up, guys? My name's a knowledge expert, and today we're gonna do some problems and learn a bit about the electric force. So, firstly, before entering anything, before talking about the electric force, let's understand a basic concept, which is called charge. So, in classical mechanics, we learn that a fundamental physical quantity that governs many bodies is called a mass. And the mass is basically the resistance to inertia when a body is accelerating. And so a mass can be attracted by gravity to another body, right? It could be a body can be attracted to another body, to Earth, right? Let's say this is Earth. It could be attracted like this, or there's another body with M2 here, and this is M1, and you're attracted also by a gravitational force. So when we want to know what the gravitational force is, we do the mass times g, which is 9.8 on Earth, right? Or if you want to know another mass, m2, which is attracted to m1, do that better. The equation for that is Fg is equal to the gravitational constant m1 times m2 divided by r squared. So the distance between them squared. But in electricity, it is a bit different because in electricity, you don't have the physical quantity mass. You can have some problems with mass, but the mass is pretty negligible at those levels. Uh, but when you want to know, how what electric forces certain subatomic particles feel, you need to talk about charge, which is denoted with Q. Charge is what mass is in classical mechanics applied to electricity. It is the physical quantity, the most fundamental physical quantity when working with electricity. So when you have a mass, you can only have a positive mass, right? Which is a positive mass. So uh, there's nothing too different. You can't have a negative mass, but in charge is a bit different. A charge you can have a positive charge. Let's put it red. It's a positive charge, but you could also have a negative charge in blue, right? You can have two types of charges. You could have them either positive or negative. Now, a positive and negative charge, just like in classical mechanics, they will attract. They will feel a force and they will attract each other. But you could also have a opposite, literally the same charges, let's say both positive, and this will be a bit special because they will actually repel. This doesn't happen in gravity, right? You can't have particles repel. They only attract. They feel a force that they will attract each other to. But in electricity, it's a bit different. The same charge, let's say if you have both positive or say with the negative, if you have both negative charges, they will feel a force repelling and not attracting, which is how an electricity works. And they will give you certain charges in problems, but they could sometimes give you the electron. They could say an electron or a proton does it. So in a problem, we could say this is 1 microcoulomb, or this is 2 microcoulombs. The most fundamental, and yes, in the most fundamental unit of measurement in a charge is called the coulomb. That is what a charge is measured in, just like the force is measured in Newton, just like the mass is measured in kilogram, the charge is measured in coulomb. So they can give you problems like 2 microcoulombs or 1 microcoulomb because it's rare that they're going to give you 1 coulomb. It can happen, or 2 coulomb, but at such small levels, you don't really have that much charge. And so what can happen is that it could give you, instead of giving you the charge, it could say that an electron or a proton are next to each other, and they interact with each other through the electric force. If so, the electron and the proton have the same scalar as charge, but they have the opposite charge, right? So both have the elementary charge E, but the electron has negative E and the proton has E. The elementary charge E is 1.62 times 10 to the negative 19. So that is how it is. The electron and proton both have the elementary charges. The electron is negative. And so when we have problems asking for electron or proton what they're doing, we're going to use this value. Now the second thing we need to know is about the electric force. The electric force is governed by something called Coulomb's law. I think I read it as, I don't know if this is how you write his name, but it's Coulomb's law. And Coulomb's law states that force, the electric force, is equal to constant K, and the constant K is given, which is 9 times 10 to the 9. And then you have times charge 1, charge 2, divided by r squared. This is the equation to know what the electric force will be. This should be really similar. This should be very familiar, right? Because this is very similar to Newton's law of universal gravitation, which is G m1 m2 divided by r squared. You have your constants here, and you have the physical quantity of the thing you want to know, right? Here in classical mechanics you have the mass, and here you have the charge, and both have the inverse square law. And so this is the force that a charge will feel when they are close to each other. So if you have two charges, this is the equation of the force they'll feel. Of course, if you want to know you could just know the force, just the scale of the force, because a force is a vector. But if you just want to know the scalar of the force, you could just do absolute value of this, and then you can know it. But instead, you can know the direction of the force. If you can calculate in what direction that force is, because this is important, because in as we saw that in electricity, two charges, if you have plus and plus, they can actually repel. So if they repel, then that means that the orientation of this let's analyze this. The orientation of this force will be that way and not this way, right? And on the x-axis, this will be positive and this will be negative on the x-axis, right? So the orientation of the force will be important, but if you do want to know just the scalar, you could just do the absolute values of Q1 and Q2. Compared to in classical mechanics, in which you'll always get, for instance, they always attract, so it's always going to be in the same direction. But in electricity, you have to be careful, because sometimes it can attract, sometimes it can repel. It depends on the charge. But you can do that. So you could calculate, for instance, if you have the same charge, you have a positive and a positive, and you have q both. So, and let's say that they're the same, you have q squared divided by r squared. And you know in what direction you could draw your force in your diagram, right? Because you could see that both are positive, so logically the force will be that way, because it will feel a force like this on the charge or on the particle. So let's do some exercises. So number 1, we have two charges. One, let's call it Q1. So Q1 has a charge of 5 coulombs, and Q2 has a charge of 15 coulombs, and they are separated of a distance of 10 centimeters. So we're lucky here because they give us in coulombs. So what is the force between them? So all we have to do here is just apply Coulomb's law, which is F is equal to K Q1 Q2 divided by R squared. As we can see, these are both positive charges. So if we can do a little diagram here. One is 5 coulombs, right? This is a little boy, and this is a big boy, because this is 15 coulombs. And so, of course, you will feel a very big force, and you will feel a smaller force of repel. But this is a bit how it is, and you are separated by 10 centimeters. We do want to convert this in meters because we will be working in meters because this is a force, and so we will need meters. So 10 centimeters in meters is 0.1. This is 0.1 meters. And so we could, so now that we have all the values that we need, we can calculate the electric force, which will be 9 times 10 to the 9 times 5 times 15 divided by 0.1 squared. And you could plug these numbers in the calculator, and it will give you a pretty big number. This is why you don't get coulombs as high, because the constant is 10 to the 9, so it will give you a very, very, very big force, right? Whereas if you have here, instead of some coulombs and you have micro or nano coulombs, then the force will be more normal. And then times 5 times 15, and then divided by 0.1 squared. And it should give you the force should be 6.75 times 10 to the 13 newtons. So that's problem number 1. It's a pretty easy problem. So let's go on to the next one. So now we have problem 2. Problem 2 says 2 charges is 5 coulombs. We have Q1, which is 5 coulombs, and Q2, which is 15 coulombs. This time, we don't know the distance, but we do know the force. Let's say the force will be 9.8 times 10 to the 12, let's say. This is the force that is felt by them. So, of course, we do have the same charges that we have in the last problem. And we do have the force. So what you do have to do here is that you do need to isolate the r. So you'll have you'll write the equation like this, divided by r squared. But you know F and you know the charges, so you could isolate r, right, by doing F r squared is equal to k q1 q2, and so r squared will be equal to k q1 q2 divided by F, and so r will be equal to square root to the k q1 q2 divided by F. So the distance will be equal to the square root. It might give you in meters. It will give you in meters, but you can, if it's a pretty small in meters, you could, it depends what the problem says. If it wants it in centimeters, you can convert it to centimeters. If it wants it in millimeters or nanometers or whatever, you could convert it, but the answer will be in meters. So you have 9 times 10 to the 9 multiplied by a charge, which is 5, multiplied by 15, and divided by 9.8, or no, 9.8 times 10 to the 12. So you could plug that in the calculator. So you'll have a 10 to the power of 9 multiplied by 9. Yeah. And then times 5, and then times 15. And then we'll divide by our force, which is 9.8 times 10 to the 12. And then we do square root of that. And it should give us, r will be something like 0.26 meters. And so you can transform this in around 26 26 centimeters. So the distance between these two charges is 26 centimeters. So that was for number 2. These are pretty easy questions. They're not that hard. All right. So number 3. If an electrical force of repulsion between two -1 Coulomb charges is 10 Newton, how far apart are they? So you have a -1 Coulomb charge and a -1 Coulomb charge. They are the same charge. We don't know the distance. We don't know r, but we know also both forces will be the same. This particle will feel the same force as this one because they're the same sort of they are the same charge basically. And so we don't know the charge, or we do know the charge, which is -1 Coulomb and -1 Coulomb, but we don't, and we know that they will feel a force of 10 newtons, but we don't know how far apart they are. Again, we'll take Coulomb's law, and we'll have kq1 q2 divided by r squared. We know that the force is 10, and then we'll have 9 times 10 to the 9, and then we'll have -1 times -1 divided by r squared. Alright, so all you have to do is just plug these numbers in the calculator. We are lucky because they do give us directly in coulombs, so we don't have to convert, but sometimes you do have to convert. Most times is that they'll give you a value like 20 microcoulombs or 1 nanocoulomb, something like that. So most of the time it's microcoulombs. So most of the times you'll have like 10 to the -6 coulombs, but here they give you directly in coulombs, so you don't have to convert anything. So it's -1 times which is 1. This will give us 1. And so you could isolate r squared first, so it'll be 10r squared. 10r squared is equal to 9 times 10 to the 9, and so r will be the square root of 9 times 10 to the 9 divided by 10. So we'll have 10 to the 9 times 9 divided by 10, and then to the square root of that. No, well, yeah. Square root. And so r will be 30,000 meters. And so that's it for number 3. Alright. Now let's get to a bit harder problems. So this is for number 4. So we'll have on a sort of Cartesian plane 3 particles. You know what? For blue will be the negative ones, and the red will be the positive ones. So Q1 is right here at the origin. It's a bit bigger, I guess. This is Q1. And then Q2 is 30 centimeters above Q1. And Q3 is right here. So Q3, Q1, and Q2. Q2 is at 3 centimeters. Or I guess you could say that it's at 3 or 0.3, I guess you could say. and this is at 0, 0, and this is at 3, 0. This is at, all of these are at 3 centimeters. Q1 is equal to 1 microcoulomb. So as I said, they will give you in microcoulombs. And you will have to convert this in coulombs. Q2 is -4 microcoulombs, and Q3 is 5 microcoulombs. And so the question is, so the 3-point charges are fixed and placed in a right triangle. What is the electric force on the 5 microcoulomb charge due to the other 2 charges? So the 5 microcoulomb one is Q3. So we want to know, due to the other charges, what is the electric force? So we have a diagram here. So let us draw the forces acting upon Q3. We only want Q3. We don't care about Q1 or Q2. They will influence Q3. What interests us is really this point particle of Q3 and the forces it will feel. So this is at 3, 0. Let's put it here because we're going to have some diagrams to draw. So firstly, Q1. How does Q1 influence Q3? Q1 is positive just like Q3. So this is the same charge, so it will have a force of repelling. Let's call this force 1, 3. So force 1, 3, or the charge 1, will have a force, will influence Q3 by having a force of repulsion on X positive axis, so by there. And then we have another force like this, because it is attracted towards Q2, in a force called Q23. These are vectors, I guess. So these are the 2 forces that influence our charge, our system. These are the 3 forces that will influence this. So now we know the distances and we know even what the charges are. We can calculate F2, F3, F2, F3, and F1, F13 and F23, and just add them up. So F23, for example, F23 is KQ1, Q2 divided by R squared. Now, for F23, what is the distance between them? So here we have 3 centimeters. Also, we should, it's very important to pay attention because this is not 3 meters, but this is 3 centimeters. This is actually 0.03 meters. We always want to work in meters. So you have to convert your data into the right units. And so this is centimeters. So here we have 3 centimeters and 3 centimeters. And we could see that this is a right triangle. So the distance here, this entire distance, is the hypotenuse of a right triangle. So we could use Pythagoras' theorem. So R23 will be equal to 3 squared plus 3 squared and the square root of that. This is the distance between Q2 and Q3. So if we do 9 plus 9, 18, and so this will be the square root of 18. So that means that here we will have the square root of 18 centimeters. And this is not in meters. So we can't take the approximate value of this and not just write square root of 18. So we could just take 4.24 centimeters. So I'll use it in actual values and not just the square root of a number, but a concrete number. And so I will transform this into meters. I'll convert it. And 4.24 centimeters will be equal to 0.0424 meters. So F23 will be equal to 9 times 10 to the 9. Notice that here, if we have this in meters, what you could have done for R23 is simply that this is squared. So if this was in meters, R23 would have been square root of 18 meters, and because it's squared, down here you'll just have 18, but it's not in meters, and so I just did that just to be simpler, I guess. And so Q1 is 1 microcoulomb, so it will be 1 times 10 to the negative 6. Q2 is negative 4 microcoulombs. I'll take the absolute value because I just want to know the scalar of the force, not the vector. So negative 4 times 10 to the negative 6. And then we divide by the square of 0.0424. 0.0424. And then you could plug these numbers in your calculator. So it'll be 10 to the negative 6 times 4 times 10 to the 6 to the negative 6. And you'll get 4 times 10 to the negative 12, and then times 9 times 10 to the 9th. And then divide by the distance squared is 0.424 squared. And the force that we will get is 20.02 newtons. So this is F23. So now we know that F23 is 20.02 newtons. Now we want to know what F13 is. So F13, let's do it here. F13 is the same thing as we did for the last thing. It's just that we know that for F13, we already know the distance. We don't have to do Pythagoras theorem because we know it's 3 centimeters or 0.03 meters. So that means that we'll have K, we will just write the equation Q1, Q2, R squared. We'll have 9 times 10 to the 9 multiplied by the charge. And so the charge of, I guess, yeah, the charge of Q1 is 1 times 10 to the negative 6. And Q3 is 5 times 10 to the negative 6. And then we divide by 0.03 squared. And then you just plug these values in your calculator. So 9 times 10 to the 9. And then we multiply by, 10 to the negative 6. To the negative 6. And then we will divide by 3 squared. And it'll give us 50 newtons. So now we know that F13 is 50 newtons. Now, we can't just add these two together and just get 70 newtons. You can't do that because these are vectors, so you'll have to do vector addition. So, what you can do is that this angle. You could calculate this angle because um you could do arctan to find the angle. So we could just calculate the angle right here. The angle will be, so we know that the tangent of an angle, so this is just some trigonometry, is equal to SOHCAHTOA, which is opposite on adjacent. We know that the opposite is 3 centimeters and the adjacent is 3 centimeters, so it'll just be arctan of, well, just 1, I guess. 3 divided by 3, or 0.03 divided by 0.03 is the same thing. So you'll have arctan of 1, which is 45 degrees. So this is 45 degrees, and then you can calculate what F23x is and F23y is. And you also need to know that one is going in this direction, so it will be negative. This will be 20.02 newtons. And yeah, so let me just erase this. So you have F23, which is 20.02 newtons, going like that. And then you could just separate this in F23y and F23x. And then you could do the vector addition. So this F23x will be equal to 20.02 cosine of 45 degrees. And so you'll have 20.02 cosine of 45, which is 14. Yeah, let's say 16 newtons. And then F23y will be equal to 20.02 sine of 45. And that'll be also 14.16 newtons, because it is sine and cosine of 45 is the same thing. And so you can know now the forces on y felt on the particle and the forces on x. If we want to know the total force on x that the particle Q3 will feel, all you have to do is do 50 minus 14.6 newton, 14.16 newtons, and that will give you 35.84 newtons. So that means it'll go this way. So generally, if we're gonna redo our particle here, let's make it a bit thicker, just like that. We have our particle here, and so it had a massive force bringing it by there, and a smaller force bringing it by here. So if you subtract this force to this force, you will have a force a bit smaller, but going this way. But you also have another force going this way, which the force total on y will calculate. F total for y will be what we just calculated, because it only has one on y, right? It's 14.16 newtons, because the vector has only one, there's only one y vector really in this. So that means that the particle, if we're going to redo our drawing here, I'm going to have the particle here, and it's going to have, yeah, it's going to have a force feeling 35.80, oh no, it's going to have a force feeling 35.84 newtons that way, and is going to feel a smaller force of 14.16 newtons that way. And so these are the forces that are going to be felt by the particle. So that's about it, guys. This is how you do some electricity and magnetism. This is how you do the electric force. These are some electric force problems that we made, and to explain how charges and introduction to electricity works. I hope you enjoyed this video. That's about it. See you.